Hi, I'm Scott Knockley. In this video, we're going to look at position and orientation. So by the end of this video, you should be able to describe the pose, which is the position and orientation of a rigid body in space. You should be able to understand the properties of a rotation matrix, and you should be able to use rotational operators. Let's first look at the description of a position. Suppose we're given a point in space. All right, this is point P. In order to describe point P, we first need to establish a coordinate frame. So this is our coordinate frame. We define our axes. We have our x-axis, our y-axis, and z-axis. And we're going to call this frame A. So the subscripts A are the axes of frame A, and we'll use the curly brackets to denote that it's a frame. Now we need to determine the projection of point P onto those three axes. So this would be our projection of point P on the y-axis. This point here would be our projection of P onto the x-axis. And then lastly, we have our projection of P onto our z-axis. So we have Px, Py, and Pz. And they describe our position of that point. So we have Px, Py, and Pz. All right. And the superscript A here tells us that this is all with respect to frame A. So for orientation, it's a little different. All right. Our robot is comprised of links and an end effector or tool, and these are all three-dimensional bodies instead of points. So in order to describe the pose of our three-dimensional object, and our pose is both position and orientation, we need to describe the position of that object and its orientation. All right. And so in the previous slide, we saw how we define the position, but now we're going to look at how we define the orientation. A convenient way to do this is to attach a coordinate system to the body and describe it, that coordinate system. So say it's frame B with respect to a reference frame, in this case, say frame A. So suppose we have our rigid body here. All right, we have our reference frame A here. So this is frame A. Again, this is ZA, YA, and this is XA. We're going to attach a coordinate system to our rigid body. So say this is XB, this is YB, and this is ZB. All right, and so now we want to describe frame B in terms of frame A. So how can we do that? Well, we know that the orientation of frame B is characterized by its three unit vectors along the X, Y, and Z axes. All right, so if we were to draw them in on this figure here, we have three unit vectors, ZB, that's YB, and we have XB. So we can describe those unit vectors in terms of frame A. All right, and what you'll get is this matrix here. All right, each column is one of the unit vectors, so we have XB, YB, and ZB in terms of frame A. We denote our rotation, our orientation, I should say, as the matrix R. All right, and we call that matrix R our rotation matrix. And this superscript and subscript notation here tells us that we're describing frame B with respect to frame A. And just a note here, we have XB with respect to A is the unit vector along the x-axis of frame B described in terms of frame A, and we have the same for Y and Z. So with these three unit vectors, we can describe the orientation. This rotation matrix comes up a lot in robotics, and we'll be using it throughout the various videos. So there's a number of properties to this rotation matrix. So suppose we take our rotation matrix R and we define the three vectors as N, O, and A. It has the following properties. The inverse of a rotation matrix is actually just its transpose. All right, and you can check this out for yourself. If you take R and multiply by R transpose, we get the identity matrix. So we know that R transpose is the inverse of R. Now, our rotation matrix, because these are all three unit vectors in our reference frame, we know that they're orthogonal to each other. So we know that if we do N cross O, we're going to get A. If we do O cross A, we're going to get N. And if we do A cross N, we're going to get O. Because they're unit vectors, all right, we know that the magnitude of them is all going to be 1. And lastly, also because they're orthogonal to each other, we know that N dot O is equal to O dot A is equal to A dot N. All has to equal to 0. All right, so these are the properties of a rotation matrix. So it's an orthogonal matrix, and it's also what we call an orthonormal matrix. So R is an orthonormal matrix, which means all its columns are orthogonal to each other, and each column is a unit vector. And in fact, because R inverse is equal to R transpose, the transpose of the rotation matrix is also, each row then in that case, is also a unit vector. So in addition to describing the orientation, we can use these rotation matrices as operators. So for example, suppose we have a vector P1, all right, in terms of frame A, and we want to rotate it about some axis K here, which is denoted by Kx, Ky, and Kz, by some angle theta. In order to do that, all we have to do is rotate that matrix P1 in terms of frame A by our rotation matrix C. And that's what we do here. And that's going to define a new point P2 in terms of frame A, which is simply our rotation matrix times P1, where our rotation matrix has this form here. Okay, so in this matrix here, you'll see we have things like C theta. Well, C theta just stands for cosine theta. S theta denotes sine theta, and we're going to use that a lot in the course. There's lots of cosines and sines, so we use C to denote cosine, and we use S to denote sine. And in this matrix, we also have this V term, and it's only we find it here, and it's 1 minus cosine theta. All right, so we can use this formulation to rotate a vector about some arbitrary axis K. Now, if that rotation matrix, or the axis we're rotating about K, is one of the principal axes of our frame, so by that we mean it's either the x-axis of frame A, y-axis, or z-axis, our matrix here reduces down to one of these forms here. So here we have the rotation about an x-axis, and we know it's a rotation about the x because we have this unit vector 1, 0, 0 in the first column. This is the formulation for a rotation about the y-axis. So you see we have 0, 1, 0 in the second column. This is our y-axis. And then a rotation about the z has this form, and we have 0, 0, 1. This is a unit vector in the z-axis. So these are rotations about our principal axes, and we can use those as well.